Hello and welcome. In this explainer, we're going to pull back the curtain on how enormous, really complex software gets made. And we're going to be drawing from some fantastic educational research by Dr. Sudhinja S.G., whose work is all about helping teachers and educators just like you get a real handle on these fundamental computer science concepts.
Okay, so to kick things off, I want you to just look at this number, 40 million. Let that sink in for a second. What on earth could that be?
Well, that is roughly the number of lines of code you'd find in a single program that many of us use every day, something like Microsoft Office. And there's just no way any single person could hold all of that in their head at one time. It's impossible.
So that leads to the big question, right? How do teams of hundreds, maybe even thousands of people build something so gigantic without the whole thing just collapsing into a buggy, chaotic mess? Well, the answer is a discipline called software engineering. It's basically a collection of smart tools and practices that lets teams build things safely and reliably, even on a massive scale.
So how in the world do you even start to tackle a 40 million line monster like that? Well, you start with a blueprint. The absolute most important principle for preventing chaos is to have a clear, organized structure right from the very beginning.
The main strategy for taming all that complexity is something called modularity. And a really popular way to do this is with object-oriented programming. Now, the core idea here is actually pretty simple. Instead of having one gigantic, endless list of instructions, you break the problem down into small, self-contained building blocks. We call these objects, and each one has its own specific job to do.
To really make this click, let's use an analogy. Imagine a big, high-level object that we'll just call a car. It represents the entire system we're trying to build. And here's where it gets really clever. The car object itself, it doesn't need to know every tiny detail of how it works. It just needs to know that it's made up of other more specialized objects, like, for instance, an engine.
And we can keep going. The engine is also pretty complex, so it contains even smaller, more focused objects, like cruise control or maybe ignition control. See what's happening? By nesting objects like this, we create this really clear hierarchy where every single piece has a very specific job. It makes the whole system so much easier to understand and to build.
Now there's a key rule that makes this whole system work. It's all about visibility. Some of the functions in an object are public, meaning anyone or any other object can use them. But others are private. They're hidden away, just internal details. And this is absolutely crucial. It's kind of like how you know you can use the steering wheel of your car. That's a public function, but you don't need to know the complex internal mechanics of the steering column. Those are private for a reason.
Okay, so if all these different objects and different teams need to talk to each other, how do they do it without spilling all their private internal secrets? Well, they use something called an API. That stands for Application Programming Interface. You can think of it as a documented contract that spells out exactly what a piece of code does without getting bogged down in the messy details of how it does it.
And this is what one of those contracts actually looks like in practice. An API for setting an engine's RPM is crystal clear. It tells you exactly what inputs it needs, the conditions that have to be met, like the RPM must be between 1,000 and 7,000, and what you can expect as an output. This contract is what allows one team to build the engine code while another team builds the dashboard code. And they can both be totally confident that their two pieces will work together perfectly.
So we have our blueprint. But how do all the different engineers actually build their parts and then fit them together? For that, they need a pretty specialized toolkit, one that's designed for teamwork. Now sure, you could write code in a simple text editor, but pretty much every professional uses what's called an Integrated Development Environment, or an IDE. This is basically the software engineer's main workbench. It's this all-in-one app that helps you write code, it'll highlight potential errors as you type, and it has these really powerful tools for finding and fixing problems.
But what happens when you have dozens of people all trying to work on the same code at the same time? Well, that's where a system called version control comes in. Think of it like a superpowered track changes for code. Everybody works on their own safe copy, which we call a branch. They save their progress in these little chunks called commits, and then, only when their new feature is ready and fully tested, it gets carefully merged back into the official main version. This is what stops people from accidentally overwriting each other's work. It's a lifesaver.
Okay. So, we've got organized code, and we've got great tools for teamwork. We're done, right? Not even close. All of this is completely useless if the final product doesn't actually work. You have to rigorously prove that the software does what it's supposed to do and that it's bug-free.
Professional testing isn't just random clicking. It's a very structured process, often visualized as the testing pyramid. The foundation,
The biggest part is built on thousands of tiny unit tests that check each individual little component. As you move up, integration tests make sure those components all play nicely together. And finally, at the very top, you have just a few system tests that check the entire application from end to end. You build a wide, strong base of small tests to support the whole structure.
You know, what's just as important as the code itself? The documentation that explains it. A good README file is like the front door to the whole project. It tells people how to get started. API documentation is the official instruction manual for those contracts we talked about. And good comments inside the code, they don't state the obvious. They explain the why, the complex reason behind a certain decision, so that an engineer, maybe years from now, can understand and maintain it.
And finally, building great software isn't just about technical stuff. It's about people. It really requires a shared culture and a set of professional habits that make sure quality and collaboration are always the top priorities.
These are some of the hallmarks of what a healthy engineering culture looks like. Every single change is peer-reviewed by another engineer before it goes in. Automated tests are run constantly on every single update. Teams agree on style guides so all the code looks consistent and is easy to read. And maybe most importantly, they follow a golden rule that the main branch of the code should always be in a working, releasable state. These are the professional habits that keep quality high and prevent disasters.
So when you step back and look at all these ideas together, modularity, clear contracts, versioning, layered testing, and a culture of review, you start to see they aren't really just about code. They are a powerful set of principles for managing immense complexity in any kind of collaborative project. Which leaves us with a final thought. Where else in our own work, or even our lives, could we apply these ideas to build better, more reliable things together?